Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to be applying our solubility rules. Let's get started. So before we apply our solubility rules, let's briefly just go over them. So my table is split into the mostly soluble ions and the mostly insoluble ions. What is important to note are any exceptions. So chloride, bromide, and iodide have these exceptions. That means these salts are mostly soluble except when these cations are present. The reverse is true for my mostly insoluble ions. So hydroxide salts are mostly insoluble except if you have an alkali metal or if you have any of these cations. So when using this table, make sure you know if you're talking about a mostly soluble ion or a mostly insoluble ion. Now let's do some examples. Our first salt that we're going to check is calcium sulfate. There are two ways to check on this. You can either look for the cation or the anion, and sometimes you'll find both. So let's look for the cation, calcium. So I don't see calcium in my first column, but I see it popping up here and here. So now I need to bring in my anion. My anion is sulfate. So I do have a rule for sulfate salts. So sulfate salts are mostly soluble, but calcium is an exception. So that means that calcium sulfate is an insoluble salt. So I am just going to put an S after calcium sulfate to indicate that's insoluble. If this is formed in solution, it's going to precipitate out as a solid. Let's look at another salt. Okay, this is ammonium phosphate. Again, we can look at cation or anion, and sometimes we have to look at both. So starting with my cation, my ammonium, I see that I do have a rule for my ammonium ion. It is a mostly soluble ion, and there are no exceptions. That tells me that ammonium phosphate is soluble. So let's write an AQ to stand for aqueous. Now, you could have also checked your phosphate anion because I do have a phosphate rule. This is under my mostly insoluble ions. And you can see that ammonium is an exception. So again, it tells you that it is a soluble salt. Finally, let's look at lead chloride. I don't have a rule specifically for lead, but I see that lead has popped up here and also here. So it looks like lead is an exception. Let's take a look at our anion. That is a chloride salt. I do have a rule for chloride salts. Lead is an exception. So instead of being soluble, this is going to be an insoluble salt. So let's put an S right after lead chloride to indicate that it is insoluble. Just as an aside, remember that these are general rules. We are not actually calculating solubilities here. But our general rules still allow us to make predictions. So let's work on equations with soluble and insoluble salts. Specifically, we want to look at molecular, ionic, and net ionic equations. So here is a very general equation given here. It's not even balanced. So before we do anything, let's go ahead and balance this equation. So I know I'm going to need a 3 here for balancing my potassiums, and that actually balances my nitrates and phosphates and aluminums are good. Okay, so at least it was an easy balance. Now let's determine which salts are soluble and which salts are insoluble. So starting with potassium phosphate. I do have a rule for potassium. It is an alkali metal. It is a soluble salt and there are no exceptions. So I can be confident that potassium phosphate is soluble. So let me go ahead and put an AQ above potassium phosphate. Now let's look at aluminum nitrate. I have a rule for nitrate salts. They're mostly soluble and I have no exceptions. Therefore, aluminum nitrate, also a soluble salt. Now for potassium nitrate, it is not only an alkali metal, but also a nitrate, no exceptions. Definitely going to be a soluble salt. So AQ here. Lastly, aluminum phosphate. I do have a rule for phosphates down here. This is a mostly insoluble salt. Is aluminum an exception? No, aluminum is not an exception. So aluminum phosphate is insoluble I'm going to put an S because this is going to precipitate out as a solid. Okay, let's rewrite our equation a little neater. Here we go. This is our molecular equation. Let's go from our molecular equation to our ionic equation. And the way we do this is we take all of the soluble salts and we're going to break those apart into their cations and anions. So here we go. This is our ionic equation. Let me show you how I got all of this. Potassium phosphate, because it is soluble, it breaks apart into potassium and phosphate. Now notice this 3 here becomes this 3 here. There are 3 potassium ions. Aluminum nitrate, also soluble, becomes the aluminum cation, and again 3 nitrate anions because of this 3 here turns into that 3 there. Potassium nitrate, notice it has a 3 here for balancing. That means we have 3 potassium cations and 3 nitrate anions. Now my aluminum phosphate is insoluble. It is a solid, so it remains the same. It's still insoluble. It does not break apart into cation and anion. Once we have our ionic equation, we need to pull out all the spectator ions. Now, spectator ions are ions that are the same on the reactant side and the product side. So if you look at my 3 potassium cations, I have the exact same thing over here on the product side. So I can take these out. Nitrates are also exactly the same on reactant side and product side. You may ask, what about phosphate and aluminum? Well, here they are ions and here they are bonded. So those are not the same thing. You cannot cancel those out. Those are not spectator ions. So I have pulled all the spectator ions out of my ionic equation. So I'm going to rewrite this a little neater. Here we go. And this is the net ionic equation. So my phosphate pulled down, my aluminum pulled down, and my precipitate, my aluminum phosphate, also pulled down. What a net ionic equation shows is it shows the reaction that is really going on. So these potassium ions here from my ionic equation, they're just hanging out in solution. They are not participating in the chemical reaction at all, which is why we pull them out of the net ionic equation. Let's do another equation. Here is my next equation that we're working with. Let's first check and make sure it's balanced. C2 lithium, 1 carbonate, 2 ammonium, 1 sulfide. We're good. Okay, so this is a 1-to-1 ratio. Perfect. Now let's determine soluble and insoluble. So starting with lithium carbonate, I do have a lithium rule. It's soluble with no exceptions, or if I happen to check carbonate, that is insoluble with lithium as an exception. So this is a soluble salt. Next, ammonium sulfide. I have an ammonium rule with no exceptions, or of course, if I happen to check my sulfide first, I have ammonium as an exception. So again, a soluble salt. Next, lithium sulfide. Again, lithium, there are no exceptions, or if you check sulfide, you would see lithium as an exception. And finally, ammonium carbonate. Ammonium is soluble with no exceptions, or carbonate is insoluble with ammonium as an exception. So again, a soluble salt. Let's rewrite a little bit neater. Here we go. This is now our molecular equation. Now let's go to the ionic equation. Remember, every salt that's soluble, we are going to break apart into cations and anions. So here is my ionic equation. They do get quite long, don't they? But let's see how my salts break apart. So lithium carbonate, 2 lithium cations, and a carbonate anion. Ammonium sulfide, 2 ammonium cations, and a sulfide anion. Lithium sulfate, again, 2 lithium cations, and here's my sulfide anion, and my ammonium carbonate, 2 ammoniums, and 1 carbonate anion. Now let's pull out spectator ions. Remember, they have to be the same on both the reactant and the product side. So let's see, here's my lithium. Do I have it over on the reactant? Yes, okay, so that is a spectator ion. Carbonate reactant. Okay, carbonate on product side, that's also a spectator ion. How about my ammonium? Yes, it is the same on that side too. Okay. And finally, sulfide. Yes, that's exactly the same. So those are also spectator ions. Now, don't panic. I know we have crossed out all of our ions because they're all spectator ions. This is because all 4 of these salts are soluble, which means there is no reaction. So when you're asked to write a net ionic equation for this situation, you almost always put NR, or you can write no reaction. So there is no net ionic equation in this case. Let's take what we have learned and apply it to a stoichiometry problem. Our problem reads, when barium nitrate reacts with potassium sulfate, will a precipitate form? If so, how many grams of precipitate will form when excess potassium sulfate reacts with 850 milliliters of a 0.95 molar solution of barium nitrate? The products of the reaction are barium sulfate and potassium nitrate. The first thing I want to do is I want to get a balanced chemical equation. So I have been given my reactants and products. I have barium nitrate and potassium sulfate as reactants, and the products are barium sulfate and potassium nitrate. So let's just get those down in an equation. Here we go. This is unbalanced and we haven't determined solubility at all. We are going to treat this just like our previous problem. Let's balance this equation and let's determine what is soluble and what is insoluble, because we need to know if a precipitate will form or if we have a no reaction situation. This is a fairly simple balance. We just need a 2 right here. Now let's determine which are soluble and which are insoluble. Barium nitrate, I know my nitrate salts are all soluble, so this is soluble. Potassium sulfate, I know potassium salts here are all soluble, no exceptions, so again, soluble. Barium sulfate. Sulfate salts are mostly soluble, except barium is an exception. This is an insoluble salt. I'm going to put an S here. So we already know we will form a precipitate. Barium sulfate is going to precipitate out. And finally, potassium nitrate. Yes, both potassium and nitrate are soluble with no exceptions. Okay, rewriting this a little bit neater. Here we go. Remember, this is the molecular equation. Let's break this down into ionic and net ionic equation. Okay, remember, to go from molecular to ionic, we're going to write cations and anions for all soluble salts. So here we go. Here's our ionic equation. You can see like my barium nitrate, my potassium sulfate, all cations and anions. My barium sulfate I keep together because that is insoluble, but my potassium nitrate comes here. Let's pull out spectator ions. Nitrates are spectator. Potassium is spectator, and that is it. So let's write my net ionic equation. Here we go right here. So this is where the real chemistry is taking place. Now let's start to deal with our math. So we want to know how many grams of barium sulfate is going to form, and we've got 850 milliliters of a 0.95 molar solution of barium nitrate. Okay, I've got concentration. Let's get our equation for concentration up. Here we go. Let's plug in what we know. I know my concentration is right here, and I also know my volume. Now notice I did change it from milliliters to liters. I can calculate my moles of solute, and in this case my moles of solute are going to be barium nitrate because this is the barium nitrate solution. Okay, so I have 0.8075 moles of barium nitrate. Now I'm trying to find my grams of barium sulfate. There are 2 ways to do this. We can use our net ionic equation or we can use our molecular equation. I will show you both ways. So first I'll show you this with the net ionic equation. To get to barium sulfate, I need to first figure out barium. To figure out barium, that came from my barium nitrate. So rewriting my moles of barium nitrate. My first mole ratio is given right here. For every 1 mole of barium nitrate, I am going to get a mole of barium. Now that I know my barium, I can predict my barium sulfate. So here's my second mole ratio, 1 mole of barium to 1 mole of barium sulfate. My final step, of course, is just to convert my barium sulfate from moles to grams. So here's my molar mass. Again, making sure everything cancels nicely, and I get 188.5 grams of barium sulfate. So that's using the net ionic equation, but we can also do this using the molecular equation. Again, starting with my 0.8075 moles of barium nitrate. I am simply going to use my barium nitrate to predict my barium sulfate. So here's my mole ratio. Again, I get cancellation, and then I just convert grams to moles, making sure my moles cancels, and I get the same answer, 188.5 grams of barium sulfate. This is another case of use the method that makes the most sense to you. Now, hopefully you understand why table salt dissolves in water. I hope you found this video helpful, and thanks so much for watching.